Every time you flip a light switch, charge your phone, or turn on an appliance, you are participating in a massive, interconnected network known as the electrical grid. But the electricity traveling to your home doesn't just flow naturally through the wires at a safe, usable voltage. It travels hundreds of miles from power generation stations at incredibly high voltages, sometimes up to hundreds of thousands of volts. To make this electricity safe for consumption, or even to transmit it efficiently over long distances, we rely on one of the most vital yet quietly hidden inventions of the modern era, the electrical transformer. These massive machines sit silently in substations and on utility poles, serving as the unsung heroes of our industrial world. Understanding how they work requires us to peer inside their heavy steel casings and explore the fundamental laws of physics that govern electricity and magnetism. When you look at a power transformer from the outside, it appears to be nothing more than a static, metallic tank surrounded by cooling fins, cables, and large ceramic insulators called bushings. However, inside this protective enclosure lies a highly sophisticated system operating on the principle of electromagnetic induction. At the absolute heart of the transformer is the core. The core is typically constructed from high-grade silicon steel, and it is not a solid block of metal as one might assume. Instead, it is made of hundreds of incredibly thin sheets of steel packed tightly together, known as a laminated iron core. This laminating process is crucial because a solid piece of iron subjected to changing magnetic fields would experience massive energy losses due to swirling internal electrical loops called eddy currents. By breaking the core into thin, insulated layers, these wasteful currents are minimized, ensuring the transformer runs with maximum efficiency and minimal heat generation. Wrapped securely around this laminated core are two distinct sets of electrical coils, commonly referred to as the windings. Made of highly conductive copper or aluminum, these coils are divided into the primary winding and the secondary winding. The primary winding is the input side, which receives the incoming alternating current electricity from the power source. The secondary winding is the output side, which delivers the modified voltage to the destination. It is important to realize that there is absolutely no physical or direct electrical connection between the primary and secondary copper coils. They are completely insulated from each other. So, how does electricity jump from one coil to the other without touching? The answer lies in the invisible, dynamic force of magnetic flux. When alternating current enters the primary winding, the constantly changing direction of the electrical current generates an equally dynamic, alternating magnetic field around the coil. Because the coils are wrapped around the highly permeable laminated iron core, this magnetic field is safely guided and concentrated through the core's path. This moving magnetic field is known as magnetic flux. As this flux flows continuously through the loop of the iron core, it passes right through the center of the secondary winding. According to Faraday's law of electromagnetic induction, when a changing magnetic field passes through a conductor, it induces an electrical voltage across that conductor. Thus, the alternating magnetic flux effortlessly transfers energy across the physical gap, generating a brand new alternating current in the secondary winding. The true magic of the transformer lies in its ability to change the voltage level during this wireless transfer, a feat determined entirely by the ratio of turns in the two coils. If the primary winding has more turns or loops of wire than the secondary winding, the voltage will be stepped down, resulting in a lower output voltage. Conversely, if the secondary winding has significantly more turns than the primary winding, the voltage is stepped up to a much higher level. This simple proportional relationship allows engineers to precisely design transformers for specific tasks, whether it is stepping up voltage to 500,000 volts at a power plant to minimize energy loss over long-distance transmission lines, or stepping it down to 240 volts just outside your neighborhood for safe domestic use. In a real-world substation environment, these internal components are supported by heavy-duty external infrastructure designed to handle immense electrical stress and environmental elements. The massive bushings protruding from the top of the transformer act as insulated pathways that safely guide high-voltage overhead transmission lines into the sealed tank without grounding out against the metallic frame. Because the process of changing voltage still generates a considerable amount of heat despite the laminated core, the entire tank is filled with a specialized insulating oil. This oil serves a dual purpose. It prevents electrical arcing inside the tank and absorbs internal heat, carrying it toward the external radiator fins where it can be cooled by the surrounding air or heavy-duty fans. A small tank mounted on top, called a conservator, provides extra space for this oil to expand and contract safely as temperatures fluctuate throughout the day. Through this harmonious combination of internal electromagnetic physics and robust external engineering, power transformers maintain the invisible lifeblood of our modern cities, working tirelessly behind the scenes to keep our world illuminated.